video, we're going to look at confidence intervals for two proportions. So when our conditions are all met, we talked about the conditions in the last two videos, we're ready to find the confidence interval for the difference of two proportions. And the confidence interval, remember, is found by taking our point estimate, which in this case it's going to be p hat 1 minus p hat 2, and then plus or minus the margin of error. And the margin of error is found by doing z star, which is our critical value, times the standard error of p hat 1 minus p hat 2. Okay, so we're going to create a 95 confidence interval for the difference in proportions of smokers and non-smokers who think the federal tax on cigarettes be raised to pay for healthcare reform. And then we also want to interpret our answer, since that's really important to do. So we already figured out p hat 1 minus p hat 2 in the last video when we were finding the z-score. So we just need to subtract 0.58 minus 0.21. And remember, those numbers just stand for 58% of non-smokers think that the federal tax should be raised, and the other number was 21% of smokers. So to find my confidence interval, it's going to be 0.58 minus 0.21 plus or minus z star. So I need to figure out, here what my critical value will be. And remember, for 95% confidence, we're just going to use 1.96. And then times the square root of my standard error, right? And my standard error, remember, was found this way. We already have the answer, but I'm just going to review again. This is going to be p hat 1 times p hat 2, and then divided by n, my sample size. So for non-smokers, it was 605. And then it was plus 0.21 times 0.79 over the sample size for smokers, which was 195. And of course, when we do this subtraction, we get 0.37 plus or minus. It's 1.96 times, remember when we did the standard error formula, we got 0.035. So it's 0.37 plus or minus my margin of error. When I multiply those, I get like 0.07. And if I do 0.37 minus 0.7, I get 0.30. And 0.37 plus 0.7 gives me 0.44. So now, let me shrink this so I can interpret it for you all. So now I want to interpret my answer. And basically I'm saying that I'm 95% confident that the proportion of all non-smokers who think that the federal tax on cigarettes should be raised is between 0.30 and 0.44 points higher than the proportion of all smokers. Or you could say the proportion of all non-smokers who think the federal tax on cigarettes should be raised is between 30% and 44% higher than the proportion of all smokers. And that's a lot, right? So I am 95% confident that the proportion, remember we are trying to estimate the population proportion, so we would say the proportion of all non-smokers who think the federal tax should be raised is between 30% and 44% higher than the proportion of all smokers. remember we're comparing two proportions, so our interval represents the difference that we would see in the two populations. So we are saying here that the proportion of all non-smokers who think the tax should be raised is anywhere from 30 to 44% higher than the proportion of all smokers. And if we had 100 random samples of the same size, we would see about 95 of them contain the true proportion. So one of the things we want to do is we want to compare what we got in our confidence interval to what we found in our hypothesis test. So I'd like you to pause for a second and think about here, how does the interval that you found in that example compare to the conclusion for the hypothesis test? So if you think about it, when we did the hypothesis test, we rejected the null, because we got a p-value of 0, and 0 is less than 0.05. So we rejected the null. And when we just did our confidence interval, we got an interval of 0.30 to 0.44. So what we need to look at here is, when we were dealing with our hypothesis test, remember the claim, the null says that there should be no difference in the proportions. And that no difference is signified by the number 0, right? So if I look at my interval, if the null were true, I should find 0 in my interval, and I don't, right? 0.30 to 0.44 does not contain the number 0. So that verifies my conclusion in my hypothesis test. Okay, if 0 were in this interval, then I should have not rejected the null, because the null says there's 0 difference between the two proportions. So here, 0 is not in the interval. So it confirms that I rejected the null. In the hypothesis test. So it's always good when you do a hypothesis test to then do a confidence interval. It helps to kind of check both ways that you're not making any type of errors. Now, of course, there is always a chance that you could still make an error, but you could always adjust your confidence interval. You know, maybe instead of finding a 95% confidence interval, I could lower my confidence to like a 90% confidence interval, or even less than that. And when you lower your confidence interval, think about what that does to your margin of error. So you also would want to think about maybe increasing your sample size if you were actually doing, a real study. Okay, please pause the video for this next problem here, and then we'll review it when you're finished. A public broadcasting station plans to launch a special appeal for additional contributions from current members. Unsure of the most effective way to contact people, it runs an experiment. It randomly selects two groups of current members. It sends the same request for donations to everyone, but the request goes to one group by email and to the other group by regular mail. The station was successful in getting contributions from 26% of the members it emailed, but only from 15% of those who received the request by regular mail. A 90% confidence interval estimated the difference in donation rates to be 11% plus or minus 7%. Let's interpret this confidence interval. So when we think about this confidence interval, if we write it using parentheses, it would be 11 minus 7, so 4%, to 11 plus 7, 18%. So we need to think about what that means, right? So all it means here is that if we were to take 100 random samples of the same size, and about 90 of them, right, it would contain the true proportion, the difference in the proportions. So we're 90% confident that of the members that are contacted by email, the donation rate will be between 4 to 18% higher than if they received it by regular mail. Based on this confidence interval, what conclusion would we reach if we tested the hypothesis that there's no difference in the response rates to the two methods of fundraising? So as we just talked about, if you look at your interval from 4% to 18%, you want to find 0. And if 0 is not in that interval, then you would have rejected the null, right? So since a difference of 0 is not in this confidence interval, we would have rejected the null. There would have been strong evidence in favor of the alternative hypothesis. So there would be evidence that a higher proportion of members will donate if they're contacted by email. Okay, let's take a look at another problem where this time we look at something called pooling. So the 2013 International Bedroom Poll surveyed about 250 randomly sampled adult residents in each of 6 countries asking about their sleep habits. Sleep researchers generally report that people who regularly use their computers or laptops in the hour before trying to go to sleep are less likely to report getting a good night's sleep, more likely to be categorized as sleepy, and more likely to drive drowsy than their counterparts. The poll found that 128 or 51% of 251 US respondents reported using a computer, laptop, or electronic tablet in the hour before trying to go to sleep almost every night. By contrast, 162 or 65% of 250 Japanese respondents made the same admission. Is this difference of 14 percentage points real, or is it likely to be due only to sampling variability? So we'll need to perform a 2-proportion z-test, which is what we did in one of the previous videos. If the null hypothesis is true, then the two groups aren't really that different. So we can think of our two samples as really parts of one bigger sample of the combined population. So overall, if we were to look at the two populations, we found that a total of 290 people who used their tablets before bed out of a total of 501 adults who responded to the question. So that overall proportion of people using their laptops before bed was 290 divided by 501, so about 57.9%. Combining the counts like this to get an estimated overall population is called pooling. Whenever we have data from different sources or different groups, but we hypothesize that they really came from the same underlying population, we can pool them to get better estimates. Using the counts for each group, we can find the pooled proportion as basically we did p hat, and we'll use the subname pooled, is just the success for the first group plus the success for the second group divided by the total of the two sample sizes for each group. So is there a difference between the proportions of US and Japanese adults who use laptops in the hour before bed? We're going to perform a test at the 5% significance level and find a 95% confidence interval. So again, we want to make sure we state what P1 and P2 here is. And I'm just going to have P1 is going to be the proportion of all US adults, and that's who look at a laptop 1 hour before bed. I'm not going to write all that out. And then P2 is just going to be the same thing, except it's going to be the proportion of all Japanese adults who look at their laptops or iPads or some electronic device within 1 hour of going to bed. So step one, I'm going to write my hypotheses. And here my null would just be P1 equals P2, right? So there is no difference in the proportions. And then my alternative is that there is a difference in the two proportions. Step two, we want to check our conditions. So the two groups are independent of each other, right? Japanese looking at their electronic devices before bed really should have no effect on the sample of US adults. I don't remember if it says a random sample. Let's look and see. Yep, 250 randomly sampled adult residents in each of 6 countries. So randomization's good. We know that they satisfy the less than 10% condition because both samples are less than 10% of all Japanese or US adults. And we also know that it satisfies the success failure for both groups as well. Okay, so it's okay to use the normal model. So let's talk about our calculations, right? This is where we would find like p hat 1, p hat 2. Since we're assuming that the two groups come from a larger same population, we're just going to pool them. And we already did that earlier, right? It's the 128 plus 62 Japanese, 128 adults plus 62 Japanese over the total number of US and Japanese. And if we add and divide, we get 0.58. So next is to find the pooled standard error. So I'll put a little subscript down here, okay, because we're pooling it here. So our formula is going to change somewhat. We're still going to take the square root, but this time for both numerators, we're going to use 0.58 and then 1 minus 0.58 because, again, we're assuming they're coming from a larger population that's the same. So 1 minus 0.58 is 0.42, and I'm going to divide that by 251 from my first sample, and then just divide by 250 in my second sample. And when you do that, you get a standard error of 0.044. Okay, so next I want to find Z. And remember, Z is going to be my p hats. So they told us in the problem that p hat 1 is going to be 51%, so 0.51. P hat 2 is 65%, so 0.65. And then I'm going to use the standard error for the pooled data. So it's 0.51 minus 0.65, and then divide that by 0.044. And of course, on the top, we're also, I'm putting this in here, but you don't need it. You're subtracting the parameter, which is 0, right? Which we get from the null hypothesis, which says there is no difference in the two proportions. So when you do this, you end up getting negative 3.18. So when I have my normal model, I know that the mean is in the middle at 0. And this time I'm going 3 standard deviations above and below. So negative 3.18, positive 3.18, and I'm shading to the right and to the left. So I'm looking for here the probability that z will not equal 3.18, which is just 2 times the probability that z is going to be greater than 3.18. So I'm going to use my normal model to figure this out. So again, second vars, and then it's normal CDF. My lower bound is 3.18, comma, my upper bound's 100, and your mean is 0, your standard deviation is 1. And then hit enter, and we get 0.0007, blah, blah, blah. I need to multiply that by 2 because it's two-tailed, and you get 0.0015. So that's my p-value. And since 0.0015 is less than my alpha level, I'm going to reject the null, right? And we're basically saying that there is strong evidence to suggest a difference in the proportion of all US adults and Japanese adults who use laptops before bed. Okay, and I'm going to verify this by doing a 95% confidence interval. Okay, so I'm going to take my point estimate, so p hat 1 minus p hat 2 plus or minus, we're doing 95%, so my critical value is 1.96. And then times the standard error, my pooled standard error, which remember we found was that. So we get negative 0.14 plus or minus my margin of error, which is 0.09. And we end up with negative 0.23 and negative 0.05. Okay, is 0 in that interval? No, it's not. So therefore, that backs up my conclusion and my decision in the last problem when I decided to reject the null. Because if there was no difference, 0 should be in that interval. And it's not. So therefore, there's strong evidence to suggest there is a difference in the proportions. So this says, and you might be wondering, like, okay, I got a negative. Like, how am I going to interpret that? So I am 95% confident that the proportion of all US adults who use laptops before bed is between 23% and 5% lower. So that's what the negatives refer to. Lower than the proportion of all Japanese adults. And that's it for that chapter, folks. Hope you have enjoyed. If you have any questions, please reach out to me, and have a great rest of your day.